Welcome back. So in last lecture we discussed about that how the deformation pattern changes if your strike and dip of the fault changes, that is the geometry of the fault, and this was one of the best example which we came across in Himalayas, where we opened up the trench across a very young active fault scarp, where we were able to see on the east facing wall there was displacement, clear displacement. On the west facing wall we had folding, and this is the slide of that, which shows and clear cut folding along a trace of the fault here. So this is the fault plane here, and we have, which is comparatively low at low angle with respect to what we encountered on the east facing wall. So this is how the variation in the deformation you will come across in different environment. So fault runs here, and the sketch, it shows that very typical deformation that is in fold bend or folding, or you can say this is fault propagation folding along the tip of the fault. Now looking at the two more signatures which were encountered along the given by Philip, which shows that E, you have the, if the surface material, so mainly if you are having the finer deposits like silt and clay, then what you will see is the formation of pressure ridges will have smoother front, which has been shown here, and may display back thrust also. So you will have the development of the back thrust. So depending on the material, that what we have been discussing, that depending on the material and the angle of the fault, you will see the different pattern of deformation on the surface. Then if you have again you will have either the formation of the back thrust and all that, or in the case you will have a very almost horizontal fault plane which is coming right up to the surface, will result into the development of pressure ridges. Then if you have an oblique component, so if the strike changes along the fault, then you may come across a development of multiple pressure ridges which are termed as N echelon. So you will have the faults which are seen here, and they are stepping with respect to one another. So in this case we have the left step over, which has resulted into the slightly thrust, as well as what we see is the strike motion. So we see an oblique tensional cracks and pressure ridges will develop. Now if we, as I have shown one example from the northwest Himalaya, that within the frame of 20 kilometers we had, like, we encountered faults, mostly thrust faults. So what we had, like, we had the frontal fault, and then we had in Pinjore Garden fault, Bursard thrust, and then we got one strike slip fault. Now along the Bursard thrust we had like slightly change in the strike of the fault, which resulted into the development of N echelon faults. Okay, so these are what we were looking at the previous one. So on the surface you will come across the N echelon fault scarps, okay, which are developed along the N echelon faults. So we have, like, within the thrust environment we came across as the faults like this. Okay, so you have one fault here, another fault here, third one is here, and fourth goes somewhere here. So this was again what we see is the left step over of the fault. So this shows slightly oblique deformation, which includes one your strike slip, and second also thrust faulting. So, this is an stereo photograph of the same area. So, you see the same feature on both the photographs on the left as well as on the right. Now, structures and evolution of thrust fault scarps, if we look at, then what we see is the finally this one. Okay. So, we have the thrust faults which are usually we take less than 45° or often 30 degrees or so, and that is again in a compressional tectonic environment. This will result into development of warp or pressure ridges during the displacement. Now, the slope of the scarp face is always less than the angle of repose. So, you will not see a very sharp scarp in such cases where you are having thrust faults. So, scarp faces I am talking about, that if you have, suppose you have an horizontally deposited sediments, and if you deform this, for example, if you are having a very sharp fault scarp which will develop of course in a hard material. So, this will not be seen in the soft one, but if you are having this face, so that what is been we are trying to explain here is that we will not see this, you will not see this type of scarp here, but rather you will be able to see the false scarp which is developed something like that. So, you will have the folding because the material is very soft, and this will be less than the angle of repose that we have discussed in the one of the lecture, which where we talked that if you are having the slope angle of the, that is the scarp slope is around 30° or so, then it will become stabilized. Now, the ruptures are usually accompanied by flexures and associated secondary minor extensional cracks. So, this we have already discussed in one of the example which I was showing was of course the secondary deformation, but that on a larger scale the mechanics remains the same. So, you have the extensional cracks which will develop on the surface of the scarp. Sometimes such displacements with steeper scarp generates colloidal wedges. So, if you are having slightly the scarp is steeper in the sense, then you will see the formation of colloidal wedges at the base. So, this was the example which we looked at in the beginning also, that we have slightly sharp steeper scarp, and then we have the colloidal material which is sitting at the base of the scarp. Few more examples. So, type of reverse fault scarps produced in 1999 Chichi earthquake of Taiwan, which shows one, the hanging wall collapsed. So, if you see here, the hanging wall is collapsed, and the whitish portion which you see is because of the collapsed material. Second is B, you have the hanging wall collapse scarp, foreground and transition into the pressure ridges. So, you have the scarp initially came, the material came on the top with a slightly sharper scarp, but then you have the scarp material which has fallen down and been dragged on the surface. Then you have the pressure ridge, typical pressure ridge scarp displacing in a smooth school running track, and then we have a complex scarp, okay, complex low angle pressure ridge scarp in soft and ductile material. So, these are few examples which shows that the pattern of deformation changes along the strike within the same environment and along the same fault in a single event. So, this is an example again of you have the material where you are having the steeper scarp for faults coming right up to the surface, and you are having it branching out gentler scarp. So, if we recall that what we discussed about the décollement or detachment in Himalayas. So, mostly the main fault systems we are having a thrust fault system. So, this is your MCT, and then you are having a branching out fault which belongs to MCT, and then you are having MBT and HFT. Now, with this what we can judge that if you recall that this is the previous slide here, if you look at that what it was been suggested that in a typical steady state model, the initial faults which were developed at the time of the collision and the overriding plate started deforming. So we had like this is the Indo-Sangpu suture zone, and then we are having MCT. So when the MCT was developed, we never had this fault system in the frontal part. So this was the frontal fault, and then progressively what we see is that deformation has moved towards the foreland. So this is your foreland side, and this is your uplands. So towards the foreland, what we see is the younging sequence in terms of the faulting events, or when the fault started moving. So the youngest one is this one. So this is HFT or HFF, because some of some researchers, they believe that the Himalayan frontal thrust, which we usually have been able to prove based on the paleoseismic studies, but in some the areas it shows strike motion. So it is better to call fault, and we should not give the nomenclature of thrust to this. So it depends on the groups to group, that how they have classified. So HFT is the youngest fault system in Himalayas. Now this can be understood well by the model which was been proposed by Weber and Cott in 1980, describing complex phenomena of thrust faulting occurring near surface mainly in unconsolidated sediments. Okay. So what it suggests that the movement along the thrust fault result into formation of pressure ridges or humps or mole tracks scarp. Okay. So first we have like movement along this fault, then you will be able to see a development of pressure ridge or a mole track, and then second, the propagation of the tectonic movement will be seen in the foreland side. Okay. So earlier it was along this one, and now it has been taken up by this fault here. Okay. So the hanging wall block slides on the former ground. So the contact between the ground here below and above, so this part will mark the contact of the former ground. So the hanging wall block slides on the former ground in such a way that the soft sediment along with the topsoil is bulldozed. Okay. So this is a bulldozing effect which is been experienced and seen in Himalayas. So in the front of the fault tip or the overthrusting block will have the bulldozed material. Now the frictional resistance along the base of the overthrusted block. So along the base of the overthrusted block. So this forms the base of the overthrusted block. It exceeds the strength of the sediments of the overriding plate or the block. Okay. Now this is one of the reason why you will see that there is a propagation of the fault. Okay. So initially it was along this one here, then it was been transferred to this, and then finally it has been moving along this one. So this keeps taking place, and so the movement is transferred. Okay. So the tectonic movement is transferred from the original master fault to second fault, which splays off from the main fault. So this is typical of the imbricated fault system. So the movement will keep on transferring from the previous older fault to the newer fault, and the deformation will keep progressing towards foreland. So this is a very common phenomena which we observe, and the reason is because of the frictional resistance along the base of the overthrusted blocks. So we performed a small experiment to understand this phenomena, and we were able to pick up the deformation pattern, which shows the fold-end propagation of deformation. So, this explains the phenomena of imbricated stacking in thrust faults. That is, the best example is your Himalaya. Now, if you look at the structures and the evolution of the reverse fault scarps, then reverse fault scarps, we usually take that the dip is greater than 45 degrees, and in case of the thrust faults, we were having less than 45 degrees. So, typically form scarps with steeper faces, and the angle of repose will be comparatively higher. So, hanging wall usually collapse after faulting. The scarp which has been formed in case of the reverse high angle greater than 45. So, you will see the collapse of the faulting here. So, scarp will with the steeper face will generate colluvial wedges. So, in most of the case areas where we are having very steep fault scarp face because of the high angle, and that is you are having the reverse fault greater than 45 degrees, then you will bound to see the collapse of the scarp, which has been shown here, this portion, and you will have the later followed by the deposition of the colluvial material. So, you can also try to go back and look at these slides or the lecture which we were talking about, that what is the importance of the colluvial deposits. Okay. You can also, that can also help in identifying the ancient earthquakes or the old earthquake signatures in the trench. Now, degradation of reverse fault scarp, similar to what we have discussed in the normal faulting environment, the phenomena of degradation of reverse fault scarps takes place in a similar way as that in the case of the normal fault scarp degradation, because the reason again will remain the same, that you have the steeper fault scarps. If you are having, then the scarp will become stabilized when it reaches the angle of repose. Okay. So, you have like 30 degrees or so, then it will be stabilized, and you will have the deposition of the colluvial wedge and the wash slope material and all that. So, very much similar to what we discussed during the normal faulting environment. So, degradation of scarp takes place by deposition of material from hanging wall, because under the gravitational slide. So, you will have the larger block sliding down on the free fault scarp surface. Okay. So, then we will have the wash process. Okay. So, studies have proved that colluvial deposits across reverse fault scarps usually shows fining upward sequence. So, you will have the coarser material first and then capped by the finer deposits. Okay. So, this part is more or less similar what we have discussed. So, the scarp studies and what we study in the trenches, the colluvial material helps us in identifying the events to some extent. Now, identification of recurrent faulting on the basis of colluvial wedges and reverse faulting environment. One example we have already looked at in the normal faulting environment. So, this is the case in the reverse faulting environment. So, what we see that the occurrence of the colluvial wedges in trench investigations are usually used to decipher number of paleo earthquakes. Okay. So, colluvial wedges we use to decipher the number of paleo earthquakes. Colluvial debris comprises rubles or collapsed blocks of the hanging wall, along with some fragments of pre-faulted surface soil. So, usually this material will comprise what has been shown here, that you will have the material from the scarp, which is also bringing the material from below, as well as you will find some blocks from the pre-faulted surface, that is your soil. So, details of colluvial wedge, if we have to consider, then what we look at is that collapsed colluvial material blocks will show disoriented stratigraphy. Now, this is important one. So, if you compare this, for example, this block here, then the structure, sedimentary structures which you will find here will not be the same, but of course it may show some sedimentary features which are absolutely not in the same pattern or the orientation. Okay, pattern may remain. For example, you are having here that slightly horizontal surface here, but here you will find that they are seen something like that. Okay, so disorientation and stratigraphy will be seen on the fallen blocks on the surface, on the base of the scarp. Okay, material will be fragile because it has been eroded from the intact blocks. So, they will be, this portion will be fragile as compared to what we will see here and on this side of the fault, on either side of the fault, and initially larger clasts will collapse, followed by smaller and finer clasts, giving rise to fining upward sequence. So, what we were talking in the previous one, that we will usually see a fining upward sequence. So, fining upward sequence, usually what we talk is that we have the coarser deposits and then kept by the finer one. So, this sequence will say, we will say is an fining upward sequence. So, you will have the coarser sediments in size, and you will have finer sediments capped by it. So, we see usually the fining upward sequence. So, there are few very important part, that we have disoriented stratigraphy which will be seen in the colluvial material, then the material will be comparatively fragile, and we will have fining upward sequence. So, we will have the larger clasts, then smaller and finer clasts, giving rise to fining upward sequence. So, repetition of faulting activity will result into repetition of same cycle of erosion. So, that means that we will keep having, if we have the similar deformation which will take place in the next event, then again we will have the formation of the colluvial wedge. Okay. So, this cycle will be repeated, but in some cases where we are having very homogeneous material, this becomes a little bit difficult. So, repeated faulting will produce stacking of colluvial wedges. Okay. So, you will have stacking of colluvial wedges, where each colluvial wedge will represent the respective or individual faulting. In Japanese literature, this has been referred as D structure. So, basically what we see is then typically D structure here. Okay. So, this has been termed as D structure, which helps us in deciphering the individual events. So, this shows the sequence of the events. So, let us view one by one. So, basically this whole this is the final one which has been encountered in the trench, and this shows that along this fault two events have occurred, and occurrence of two colluvial wedges. Older wedge has been cut by the second event. So, let us see that. Okay. So, first earthquake resulted into the formation of this scarp, and the movement was been observed along the branching out faults also, which displaced the soil here, as well as it has displaced the soil here also. Okay. So, the maximum displacement. So, this is the major fault along which the displacement took place, and then followed by the erosion. So, you will have the deposition of the colluvial wedge here, and after this then finally what you will have is the slope and the finer material coming and depositing and stabilization of the free face of the scarp. So, you will have the capping of that, and then finally you will see that there is a deposition of the layer here which has been shown. So, next soil layer has been shown here. Okay. So, until day what we had, like, so if you compare this, then we had the earthquake took place after after the deposition and the formation of this soil, and then capped by the colluvial material, and then the next phase of deposition and the formation of soil capped this whole sequence, that is the sequence of faulting as well as the colluvial material. Another earthquake along the same fault and also the second subsidiary branching out faults, what we see is that definitely this will displace the whole sequence here. So, it will displace this portion as well as it will displace this, and that what is been shown here. So, you have again the displacement of on the same fault, resulting into the displacement of the hanging wall here, and the colluvial material which was sitting here also got displaced, as well as the soil which was formed, final capping was also displaced here. And then again there will be in phase of the deposition of the colluvial wedge because of the erosion of the or the collapsing of the steep scarp here. So, this is the second colluvial material which or the second colluvial which was formed, and compared to the what we were looking at the first one. So, again the same process takes place, and we have the formation or the deposition of the soil here, and the deposition of the material and the formation of the soil. And finally what we see is this one. So, you have the sequence coarser, finer, and then capping of the soil here. So, during the next another event, if you envisage that there will be another event here, then you will have the displacement of this whole sequence. So, again another. So, you have the first colluvial wedge here, and this is your second colluvial wedge. So, based on this also you will be able to judge that at least there were two events along this fault. Now, this is the trench which we opened across one of the young fault in Himalayas, which shows the comparison between the GPR profile which we took and the exposed sequence in the trench. So, if you have the deformation along very low angle fault, then the pattern of deformation will be different. Okay. I will stop here. We will continue in the next lecture.